அனைவருக்கும் வணக்கம். Today we are going to see what is the ferrites, and then what are the characteristics of ferrites, and then what are the structure of the ferrites. So these are the things we are going to discuss. The ferrites, it's a kind of, or it's a type of ferromagnetic material, types of ferromagnetic material. Uh, it is called ceramics. So magnetic ceramics or ceramic magnetic material. The nearby spins of the ferrites are, it will be opposite to each other, but with a different magnitude. So the neighboring spin of the ferrites, near the neighboring spins of the atoms in the ferrites of the atoms are aligned anti-parallel to each other with different magnitude. So what it will be looking like that? Suppose if you are look at the ferrite material, if you look at the first spin, the magnitude will be larger. The second spin, the magnitude will be smaller, but it will be opposite to the first one. Suppose if you look at the next spin, it will be large with the magnitude, then the next one is short. So it will be like that. So the resultant magnetic field without any external magnetic field or applied field, there is a net resultant magnetic field. And that means in the ferrite in the free state, it will be show this, good magnetic behavior. So this is about the short introduction about the what do you mean by the ferrites. Now we can look at what is the ferrite structure. The ferrite structure in general, it is called spinal structure. Spinal structure. What do you mean by the final structure means? It is having 8 FCC unit cell. So the ferrite structure, it has 8 FCC unit cell. That means the single ferrite cubical cell or single ferrite the unit cell having 8 FCC inside it. So 8 face center cubic crystals. So already we know the number of atoms in the FCC. In FCC, it is equal to 4. Then the total number of atoms in a unit cell of ferrite equal to, it will be 8 times 4, it is 32, but it is not actually right. I will say why it is not right. Because the total number of the anions, it will be 32. Here in general, the FCC structure, it will called in the ferrite structure, it's anions. So 32 anions. So what do you mean by the spinal structure? It is having 8 FCC units. Okay. What are the types of final it is exist means? It is there are two types of final exist in ferrite. Two types of structure exist in the final, in the regular, in the ferrite structure. So it has two form. One is a normal spinal. The first one is a normal spinal structure. Next, the second one is the inverse spinal structure. So there are two types of spinal structure exist. One is the normal, the another one is the inverse spinal structure. What do you mean by the normal spinal structure means? So suppose if you have the FCC atom in the normal spinal structure, there are eight FCC units in the single cubical box in the single final structure. So each FCC having the each FCC have there are octahedral sites as well as the tetrahedral sites. Each FCC having eight tetrahedral sites, tetrahedral voids or sites, voids. So then the same manner, the each FCC structure have how many octahedral sites means four octahedral sites. Voids. So in the normal spinal structure, now we have discussed about the in general the spinal structure. In the normal spinal structure, how it will be looking like that? If you are asking the molecular formula, it will be looking like that. A B2O4. This is a general formula for the normal spinal structure. Here A can be any metal ion. Maybe it should be the divalent metal cation. The B is any metal ion, but that is a trivalent metal cation. The O is oxygen, that will be a divalent anion. Inverse spinal structure, it will be little bit modified form, but the B2, 1B, it will be coming outside AB, O4. It will be similar, but different form. So here, this is the inverse spinal BABO4. The normal spinal is AB2O4. Both of them are having 8 FCC in the single spinal structure. So each FCC having 8 octahedral voids, 4 so for 8 tetrahedral voids, 4 octahedral voids. This is the thing we need to remember about the uh, spinal structure. Example for the normal spinal structure. The normal spinal structure I have told A, B2, O4. If you look at the normal spinal structure, what are the example? We can say it will be the magnesium Al2O4. This is one of the example for the normal spinal structure. The next one is Mn3O4. The next one is zinc ferrite Fe2O4. These are the example for the normal spinal structure. So, the inverse spinal structure BABO4. The example, if you look at the example Fe3O4, then CO Fe2O4, then nickel O4. These are the example for the inverse spinal. This is the normal spinals. This is the inverse spinal. So these are how about the few example of the spinal structure. So each FCC structure having the 6 face center points. These FCC points are occupied by the axis and anion. So here I want to say a few comments. In each FCC, the each FCC lattice points occupied by the oxygen anion. So that means if you look at the phase center, each phase center having the oxygen anions. Already I have told FCC structure have the four tetrahedral, eight tetrahedral wise. Tetrahedral means suppose this is if a empty place is there means there is a four ions surrounding this empty space. So here the divalent the first element is a divalent cation. This divalent cation, so the first example Mgl2O3, the divalent cation, the Mg, it will occupy the tetrahedral voids. But what fraction it will occupy means there is a 1 by 8th fraction, 1 by 8th of the tetrahedral voids in your unit cell, in a FCC unit cell, occupy by the divalent metal cation. So this is one of the example, because if you look at the FC structure, it will be looking like that. Suppose I will show at the third slides how the structure will be looking like that tetrahedral voids. So how many unit cell means there is I have told the 8 FCC structure, each FCC structure 1 by 8 fraction of the metal cation, divalent metal cation it will occupy. How many of the tetrahedral voids in the per FCC means 8 tetrahedral voids. So if you are cancelling each other, then it will give the total number of divalent, the tetrahedral sides or the divalent metal ion in the unit cell is 8. So here the next voids I have told octahedral voids, about the octahedral voids. So per FCC, how many octahedral voids already I have told means 4 octahedral voids. So each octahedral in the 4 octahedral void, 1 by 2 fraction of the octahedral voids is occupied by the trivalent. This aluminum is called the trivalent metal ion. So this trivalent metal cation, it will be occupy 1 by 2 fraction, half of the fraction of the octahedral voids. So octahedral voids it will be looking like that. How the suppose this is a void means empty place. There is a 3 atoms. Then if this kind of empty place is there inside the structure, then that is called the octahedral voids. How many of them exist per unit FCC means there will be 4. So how many fraction it will be occupied by the trivalent metal ion? So the trivalent metal cation occupy the 1 by 2 fraction, 1 by 2 fraction of the octahedral voids. So how many of the trivalent metal ion per units per the spinal structure means there is a 8 FCC per spinal structure. How many fraction it will occupy means each unit cell 1 by 2 fraction. How many of them will be exist means how many voids will be there means 4 voids. Suppose if you simplify, it will give the 16 trivalent metal cation per the spinal structure. Then one can easily tell how many oxygen anion will be there means the oxygen anion it's equal to 32 because per FCC because the oxygen onion occupy only the FCC lattice sites. So there is a 8 FCC. Each FCC is having 4 atoms per FCC, 4 oxygen anion per FCC because it's FCC having 4 4 atom per unit source. So the FCC site is occupied by the oxygen. So 4 oxygen anion will be there per FCC. In 8 FCC, 8 into 4, there will be a total in 32 oxygen anion will be per spinal structure. So 32 oxygen anion per spinal structure, 16 the trivalent metal cation, then 8 divalent metal cation. This is called the normal as well as the inverse spinal structures also. Maybe it will be different for the inverse spinal structure. I will say at the end of the lectures. Now, how the crystal structure of the final spheroid. Here, if you look at this structure, so here you can go through this structure. The tetrahedral site already I have told it is this is a tetrahedral site. This is occupied by the tribe. Example in the Mn2 plus the divalent metal ion, it will occupy the tetrahedral sites. So where it will be in the this is a FCC structure. They have shown only the tetrahedral as well as octahedral sites. If you look at this tetrahedral sites, look at this structure. This is the tetrahedral sites. So there is a one atom here. There is a one ion here. There is one ion. So it will be surrounded by the tetrahedral kind of structure. So this is a oxygen ion, oxygen anion, oxygen anion. It is surrounded by the oxygen of four oxygen anion. There is a center is empty, that is called the tetrahedral voids, that is occupied by the Mn2 plus, the divalent metal cation. Similarly, the octahedral site structure is shown here. The center is the voids. It is occupied by the Al2 3 plus the trivalent metal cation. This trivalent metal cation in the ferrites ferrite compound, it will occupy the octahedral sites. It is surrounded by the 6 the anions. See, suppose here 1, 2, 3, 4, 5, 6. Where the structure will be there means if you if you look at the B sides of the ion, that is the cation. Suppose I can take the example to explain here. We can take this one. This one, if I am taking, it is occupied by 1, 2, 3, 4, 5, 6. So in general, there is a total. Sorry, here 1, 2, 3, 4, 5. This is not 5. This is 6. So in general, there is a 6 anions surrounding the octahedral voids. So that octahedral voids is occupied by the trivalent metal ion in the spinal structures. So these are the few basics about the structure of the spinal structure of the ferrite. Then we can look at the property of the ferrite as well as the applications of the ferrite. So if you look at the properties of the ferrites, we can zoom in. Yes. What are the properties of the ferrite means? Have the net magnetic moment because there is upspin. Suppose if you look at here, there is upspin with a larger magnitude, downspin with a smaller magnitude, then upspin, then downspin, then upspin, then downspin. So if you are calculating the resultant net magnetic moment, the strength of the upspin is here large compared to the downspin. There is a resultant magnetic moment in the upward direction. So that's why having a net magnetic moment. It's a first property. Next one, Above the Curie temperature, it will act as a paramagnet because if you increase the temperature, the magnetic moment it will be disordered. It will be acting like a paramagnet. If you below the Curie temperature, if your temperature well below the Curie temperature, it will act as a ferromagnetic material. So that is a thing we need to understand. Next is the susceptibility of the ferrites. It will be large. If you look at the third point, the susceptibility of the ferrite is very large and positive value. How we can represent the susceptibility value? The fourth point, if you look at the fourth point, the chi equal to the Curie constant divided by the temperature plus or minus Tn. In general, it is represented by the neat temperature. Even we can say above the neat temperature, it will be acting like a paramagnet. Below the neat temperature, it will be act as like ferromagnet, or it will show the ferrite kind of properties. The fifth point it will say is, if you look at the fifth point, mechanically it is having pure iron character. So it will be like a good mechanical property. Then, if I look at the sixth point, have high permeability and resistivity. So that means it is having the it will permit the magnetic field easily, as well as it will show the high resistive property. That means it will be a poor conductor of the electricity. Then they have low eddy current loss and then low hysteresis loss. If you are drawing the hysteresis curve, it will be not huge one. It will be kind of less, so we can put them as a soft magnetic material. Then the hard soft ferromagnet, hard back ferromagnet. It will be a soft under the category of soft ferromagnetic material. What are the advantages if you look at that? The efficiency is so high because it is used in the application of the memory device, and then cost is low. That's the one best advantage. Then we already saw it's a low eddy current loss. So eddy current loss will be minimum. Then it is having, because it's having low hysteresis loss, easy to manufacture. That is another advantage. Then occupy the low volume. Even you can use like micro devices to store micro memory devices. This is a few advantages about the ferromagnetic material, ferrites. The disadvantage of the ferromagnetic material, ferrites, what if you are asking? The first point, high recording time for storing and retrieving the data. Because if you look at that one, how it will store the retrieving the data, it is another depth concept. We are not going into the depth. So it is used a Mantos extent principle for storing and retrieving the data, but it will be too slow process. So if you look at your hard disk, you will feel the how much time it will take compared to the charger coupled device. So it requires a interface circuit. Without the interface circuit, you can't store as well as the retrieve the data and the ferrites. Slow access speed. These are the main disadvantages of the ferromagnetic material. If you are asking the applications point of view, they are used to produce the ultrasonic waves. Here, actually, it is used the Mantos Dixon principle, not in storing and recording the data, but here they the Mantos Dixon principle, what it will do, it will compress. There is a change in volume. During that time, the ferrites produce ultrasonic waves. Then it is used in the audio and video transformer. Ferrites are having the applications. The ferrite stars are used in the radio receiver to receive with high sensitivity. So it is used in computer and data processing system. These are the used in paramagnetic amplifier so that it will produce a low noise figure. That means it will take the input, it will produce output with a low noise. So these are the few applications of the ferrites. So we have today lectures. We saw the structure of the ferrites, and then we have discussed about the spinal structures. Then we saw the advantage, disadvantage, and then its application. Thank you.